We have compaction and diagenetic structures. Diagenetic means associated with the genesis or the formation of the rock. It's compaction-driven, pinch and swell structures, compaction, facility and parting, and Lysegang banding. Lysegang banding. Bands where impurities have dissolved, they're usually of different colors, and differentiated. Alternating colorful bands of redox reaction bands, such as iron and other elements, and they're not always parallel or related to bedding. We have soluble minerals that are removed by dissolution in the soluble clay minerals called stylobites. That's a stylolite. Overburden on sand. Here, in this case, the sand on top, where it is heavier, causes the sand on the bottom to become pinched and swell in structure. This indicates tensile compression stresses, usually referred to as tectonics. We have stress or compaction. Usually shales and muds have planes of parting, and this is facility. Contemporaneous structures means structures that had occurred at the time of deposition, such as debris flows and slumping. Clasts or sedimentary deposits or depositions. Here we see a mountain with the debris flow that occurred at the same time. It is a paracontemporaneous structure. Debris flows is poorly sorted, unlike a turbidite. Slumping folds due to forces like gravity, not due to tectonics as seen in other beds, and they are folded. We have salt structures, halokinesis, moving salt due to gravity. We have upbuilding and downbuilding. In upbuilding, salt gets less dense as it sinks. Salt is an evaporate and is common in sedimentary areas. The salt rises above the beds that have been laid above it with the sedimentary deposits as more layers are added. So the salt never reaches the surface. This is called downbuilding, and we can see its progress over time. In upbuilding, the overburden is crushed salt and its pebbles. The overburden is salt and it bubbles up and distorts the bedding above it and causes faults. And then there are different types of salt structures, such as a salt bulb, a salt diapier, and salt tongues. This is a rift valley with tectonic movement to the right. This is a basin that fell below sea level. The seawater filled it up. The seawater evaporates, and in the end, you get much salt buildup. And that's a sedimentary basin. We have fault structures and related features, such as gravity-driven faulting and folding. We have listric faults, rollover folds, and intrusive faulting. In the listric faults, they are made of salt, and the salt is soft, so it tends to fall down, as in this picture, or have rollover folds. Here's a salt diapir. As the salt diapir is pushed up through a formation, it will cause complex fractures. Salt rises due to its ability to change its density as it rises. Igneous structures, such as hypabyssal, a shallow underground volcanic structure, such as a stock, or a dike, or a sill. Here, crystallization is faster. In this case, we are looking at a dike swarm. The direction of greatest principal stress, sigma, is downward. The direction of least principal stress is to the sides. And we get a dike swarm with intrusion at depth forming. Notice the dike swarm is vertical. The dike swarm on top, or looking down on a volcano, forms radial dikes or ring dikes, complex stress arrays. There's autobrecciation, the dark chunks of magma that have cooled somewhat, floating on the hotter lava, autobrecciation. And you've seen photographs of this where in magma on top of a volcano, on top of the red rock are darker rocks that are in sections. Pahoehoe is thicker, slower moving lava. Is faster. We see this in Hawaii. Pillow basalts are formed underwater. Ignimbrites are the ash on the ground from the cloud of ash blown out of a volcano, such as a composite or a stratovolcano, blowing out not only lava, but also plumes of ash. Those ashes form rocks which are strewn great distance. They're heavy and they're strewn great distance away from the caldera or crater, and they are ignimbrites. Flow foliation. Rhyolitic lavas with high silica content show flow foliation. Differential crystallization in heterogeneous media. As the magma freezes, it shows a columnar jointing with hexagons. You can see this in road cuts. Impact structures such as craters, shatter cones, pseudotacholites, and shock metamorphism and stishovites or quartz formed from heat and pressure of impact. Injected glass and melted impact breccia, as when a rock has been exposed to a strong force immediately, a bang. Pseudotacholites are formed from this type of impact. We have impact structures such as a crater with an overlying crater profile. We have overturned beds from the whatever this may be, such as a meteorite hitting the ground and subsequent sediment that has re-entered into the crevice. Layers of breccia often underlying the beds. Stress and strain. Stress is a measure of the forces acting on a rock, and strain is a measure of the deformation that occurs in response to stress. So we have a body that is falling and hits the ground. When it hits the ground has a force upwards that instantaneously or almost instantaneously stops the velocity of the acceleration of the rock acting on the rock as the ground pushes back. This deforms the body. Body forces are exerted by a body and are proportional to the mass of the body. Surface forces are capable of accelerating a body and deforming a body, unlike a body force. Stress is described in vector components. We have normal stress and shear stress. Normal stress is sigma sub n. Shear stress is sigma sub s. Normal, perpendicular to the plane. Here's a two-dimensional view of it. It results in two vector components. And it gets more complicated in a three-dimensional formation, a structure or diagram, rather, I should say diagram, showing those stresses in the XYZ coordinate system. The stress ellipsoid and stress ellipse. They can accommodate infinite planes. An ellipse is in 2 dimensions, and an ellipsoid is in 3 dimensions. Isotropic or anisotropic. Sigma 1 is always our greatest direction of stress. In a two-dimensional diagram, we see the stress ellipse, where stresses, an infinite number of them, can be represented on a two-dimensional circle diagram, aiming toward the innermost part of that circle. Isotopic stresses, as in spheres, are in all directions, and the stress ellipsoid can account for greater detail on the types of stresses inside of a rock or mineral. Stress in the Moore diagram. Stress on a plane can also be visualized with the Moore diagram in an XY coordinate system. Well, in this diagram,